Okay. Hi everyone, I'm Andrea. I'm another PhD student from NP in Munich. I work with Ariel Sanchez, and I said, why not show the second time? Why not showing this GIF for the second time in the span of 10 minutes since it's so nice? So I'm going to talk about evolution mapping and what happens when we take its consequences in the nonlinear regime, and what can it help us learning about the Halo mass function, and particularly in building a new semi-analytic model of the Halo mass function. So we have this clever split of the cosmological parameter space in two groups, which are the ones that do what AS does. They shift the power spectrum, the linear power spectrum up and down, and the ones that do the more complicated stuff. They change the shape of the power spectrum, like an S or the physical matter densities. So the ones that do what AS does are the evolution parameters, and at the level of the linear matter power spectrum, their effect is completely degenerate. They can be just summarized in one number, which is the amplitude of the linear power spectrum, which for everyone who's into large-scale structure or just is trained in cosmology, is sigma 8. Except the sigma 8 won't work in this case, because the scale at which it is defined, which is 8 over h megaparsec, depends on h, which is a mix of shape and evolution parameters. And this is how this sigma 12, this quantification of the clumpiness of the universe, was born, based on a scale which is a fixed number in megaparsec, not over h. And this will give us a proxy time variable to characterize the clumpiness of our universe, the growth of structure, and thus see how the Halo mass function evolves with it. What happens, though, if we consider the actual matter power spectrum, the nonlinear matter power spectrum? And this was the original motivation to run the Aletheia simulations that were developed in our group, especially by Matteo Esposito and Andres Ruiz, and that were already mentioned this morning by Simone. These represent 9 different cosmologies, all sharing the same set of shape parameters, but with different and even very different values for the evolution parameters. So they will all get to the same linear power spectra, but through very different formation histories. And we want to collect snapshots from these simulations, not matching their time or their redshift, but matching the clumpiness that we just defined. So we have snapshots at equal values of sigma 12. The linear power spectra of these snapshots are the same by construction. What about the nonlinear ones? We see that evolution mapping is nearly exactly inherited at the nonlinear level, but not really exactly, because if we look at late times or high sigma 12 and small scales, we see some discrepancies. These discrepancies would not be there if there were something similar to what we do in perturbation theory, in which the nonlinear matter power spectrum is described as only a function of the linear one, neglecting the cosmology dependency of the kernel. There are very good reasons to do that if we stick to semi-linear scales. But once we get into the very nonlinear regime, this doesn't hold anymore. And we need to consider the cosmology dependency of the kernels, which depend particularly on this ratio here, x, given by the matter density parameter at a given time divided by the logarithmic growth rate squared. This is a parameter that we can try and exploit to describe how the Halo mass function evolves with different formation histories in two cosmologies sharing the same linear power spectrum, but different formation histories. Along with these simulations, we want to have a sort of zoom in, a higher resolution run of a lambda CDM cosmology. So we take our Aletheia model 0, which is our reference lambda CDM based on the Planck 2018 values of the cosmological parameters, and we run more boxes of it with more particles. This gives us a bit more view of what happens to the Halo mass function in a lambda CDM cosmology, and it allows us, given that we have different box sizes, to test the convergence of the Halo mass function in a nice way by matching it box to box. And if we measure it in our simulation, so we run our Halo finder, Rockstar in our case, we clean the Halo catalog, we bin it in bins of mass or whatever you want, and we take their distribution, we get this. So we have our number density distribution of Halo that we can try and model in terms of the multiplicity function that is universal if we take a very simple model like the spherical collapse. And it's described in terms of the peak height, nu, already introduced yesterday in a couple of talks. we see that it's not universal, but this was known before. It's not really universal. If you look at it in an n-body simulation, we see that it has a time scaling, and there is a quite discrepant deviation that can get of order 10 or 20% from the most commonly used prescription in the literature for it, which was the one given by Tinker and collaborators in 2008. There is a time dependency. It's not surprising that there is also a cosmology dependency, and indeed, if we look at the mass function in the Aletheia simulation, we see that different formation histories lead to different mass functions, even at snapshots that have the exact same linear power spectrum by construction. And these deviations can also get of order 10% more or less. Bear in mind that the red line that you see is a very extreme case, is a cosmology with an Einstein de Sitter cosmology, so very deviating from the universe we're used to. We can try and describe these discrepancies in terms of X, as I introduced before. Actually, we want to account for the whole history of structure formation. So we will use a modification of X. We will integrate it with a Gaussian kernel, which is centered at the time, our now time, the time at which we evaluate the snapshot, and its width, which will be a fitting parameter of the model, will indicate us how reminiscent our Elo mass function is about the history of structure formation in that given cosmology. Along with this, there is another parameter that has emerged in recent years, especially in this work by Ondaromagea and collaborators 2022, that governs the halo mass function, and it's the local tilt of the power spectrum. It's how tilted the power spectrum is at the scales relevant for your halo formation. Okay? And we can characterize it with the logarithmic tilt of P of k or of sigma even better, because sigma doesn't have wiggles. It's better behaved as a function. We actually find, this is a tiny detail, but still important, that we can get a better fit if instead of using the tilt at the scale of each halo that we see, we use the tilt at the scale which is the typical scale of halo collapse at any given snapshot. So at any given time in cosmology, we take where is nu equals 1 as a scale, and we evaluate the tilt there. So we have these three parameters now that we can mingle with to build a semi-analytic model of the halo mass function. Nu, of course, the original one. This X integrated, which tells us what happens in case of different formation histories, and this N effective just introduced. I won't show you the exact shape form of the halo mass function because it's not out there yet, but it's going to be out very soon. So in case you're interested in using it, please stay tuned and get in touch. So this is the plot you've already seen. The way we define the halos here is 200 times the mean co-moving matter density of our universe. That's our overdensity threshold that I'm showing here. This is the residuals relative to Tinker's prescription, and this is what happens if we try a refit based on our evolution mapping parameterization. This needs a zoom in, and you can see that the deviations that we get are of order 1%, 2% tops. Just in case you were wondering about which masses this corresponds to, this is the same plot. The lines are mixing a little bit because the conversion is time dependent. And you can see that we are spanning almost 5 orders of magnitude in mass. So the mass coverage is very wide. Yes, this is all lambda CDM, though. What about the different cosmologies, the formation history dependence that we mentioned? And here you have the same comparison. The dashed lines are the plot you've already seen, residuals to Tinker et al. 2008. And the solid lines are residuals to our new fitting function, percent level accuracy again, over a crazy wide range of evolution parameters. The values that we select in the Aletheia simulations are way excluded from the observational perspective. And again, very good, but this is all the data that we have used to calibrate the simulation, right? So this is the residual with respect to what the halo mass function has already seen while calibrating. What about we bring in a new set of measurements? And let me introduce yet another set of simulations, the Aletheia EMU. This is actually a subset of them. They were actually run to build emulators like the one that Alejandro mentioned before. I hope that this will be one of our next steps. Since we have this many simulations, it would be nice to build an emulator also of the halo mass function and of halo statistics in general. But just by using this subset, features different evolution and different shapes of the linear Poisson spectrum. So the parameter space that we're opening up is wider, dimensionally speaking, with respect to the previous ones. We still retain our percent level accuracy over a wide range of redshifts, or sigma 12, if you want, and a wide range of masses. Now, we're getting close to having a tool that can give into the community and used in any kind of studies on large-scale structure that need to use a halo mass function. But to make it actually usable, we need to extend it to other halo definition. It can't just be 200 times the mean density. It needs to be adaptable to other halo definitions as well. And of course, we can rockstar our particle catalogs again with different halo definitions and refit it. And this is what we get. The plot is a bit crowded. You have Aletheia mass and Aletheia together in each panel. So there is a bit of superposition, but the main thing is that the residuals that we get are still very good. They tend to decrease in quality a little bit as we go up with the overdensity threshold, because this is what happens to your halo mass function measurement. As you go up, you go to the inner and innermost part of your halos, it becomes more and more difficult to get a converged measurement of the halo mass function. And this difficulty reflects in the fitting procedure then. But we retain a 5% at most level accuracy, which is a very good accuracy for a halo mass function model, especially at these overdensities. So with this, now we have a lot of fitted parameters for different catalogs. We can interpolate them, and then that's it, right? We test it, and we're ready to give it to the community to use freely. What can we test it with as a final check? We have the virial overdensity catalogs. The virial overdensity is not defined as a fixed multiple of the mean comoving matter density. It's defined, we define it by this formula that was given in Bren and Norman 98 for the first time. And it spans a wide range of overdensities from the classic 178 value of the Einstein-Sitter universe up to 600 or 700 for the latest snapshot of the Aletheia mass. And if we do this, we can compare it with the most commonly used prescription for a virial f of nu, which is the one given by the Spali and collaborators in 2016. This is the residuals of our measurements to that prescription. 10%, 20% discrepancy in the worst cases. If we refit it, well, we're not refitting anything here, actually. We're just testing the interpolation of our fit on this data that has not been seen by the function while calibrating. We get something that is well within a 5% shift. It gets to a 5% shift in the worst cases, and it's within 2% in the vast majority of cases over a wide range of cosmologies with very different formation histories. So we're almost ready. Top thing to do, not listed in the summary slide, is publish the paper, and then it will be available for everyone to use. And we believe this is a very nice tool, a very nice byproduct of this evolution mapping splitting of the parameter space, which allows us to characterize which are the most relevant parameters to describe the large-scale structure statistics. And with this, thank you for your attention, and I'm happy to take any questions.
Your reinforcing thought, is there any question?
So there was a discrepancy for large mass halos, even within our box. Like the figures that you were showing there, now even before that. Maybe that was also one of them. Yes, maybe can move the next slide. Yes, do you have a next slide?
For the high mass part,
like for large new, not even like for delta 150B. For large new, you see that the
I mean, for at low masses, I'm not really worried. It's still a sigma, right? So you expect, if you have a lot of points that you're presenting, you expect to have some deviations. The high mass tail of the halo mass function is quite dictated by the fact that the linear density field is very Gaussian. And it's a Gaussian cutoff. Okay, this is true in all sorts of analytic or semi-analytic model of the halo mass function. What happens at higher density thresholds where we have kind of a systematic trend that goes down to 5-ish%? I don't really know. It's a bit difficult to measure the halos at those lower densities at such early times. So like I don't have a full explanation ready, but it's probably the quality of the measurement that is degrading a little bit rather than the fit itself.
You remove subhalos from the samples?
Yes, we clean them and we remove all the subhalos that are centered within a parent halo. Okay, so if you have a big halo and a small halo close by, and there is a partial overlap between them, they can stay. But if the small halo is centered within the parent, we remove it.
But Rockstar has, itself identifies the subhalos, so why not just bring it based on Rockstar? Is it the one that you explained is based on Rockstar?
Yes.
John Pico.
We're often interested not just in how many halos there are, but their internal structures. So have you similarly tried to look for non-universalities and things like concentration mass relation? That would be really helpful to have.
Not yet is the true answer. It's a bit more complicated to measure, but it's on the other hand true, and it would be very, very interesting. So the possible lines of work after this are an emulator for the halo mass function, as I mentioned, but also looking at the internal structures of halos. We discussed with my supervisor a couple of times the possibility of building a concentration mass relation or the linear bias, which is yet another different thing. Yeah, not yet. It is true that every non-universality of the halo mass function can be rephrased into a non-universality of the profiles. So if you like, one should kind of be specular to the other, but it's something that I hope to look into in the future.
Okay. Thank you again.